Okay, so I think we will get started. So in this lecture, we are going to look at some lower bounds for kernel results. That is, that we are going to rule out polynomial size kernels for certain problems using the machinery we developed yesterday. So let me start with recalling what a composition is, or what is it we have to do to prove certain problems have no polynomial size kernel. Okay. So you have a parameterized problem Qk, and you want to argue that this problem does not have a kernel which is polynomial in size of this parameter k. So what is it you have to do? So the composition machinery, the Fortner-Santhanam lemma, all of them show the following. You start with t instances of some NP hard problem. It could be the same problem, it could be a different problem. And this notion of polynomial equivalence shows that you can make certain assumptions about these instances. Maybe all xi's are same, and maybe more things about them. They all have the same something. Yep. And we want to reduce to this parameterized problem. What is it you're allowed? You're allowed polynomial in summation xi time. And the key thing is that you want this parameter k to be at most polynomial in max of these input sizes. So this is the important restriction, that in particular, and okay, so we are this parameter, we don't want it to depend too strongly on t.
We assume that all inputs will be same, right?
Yeah. So I mean, in the more general version, there need not be, but yeah, otherwise polynomial in the input sizes. But yeah, examples we are going to look at, and so you can assume they are all the same size. And we want it to depend on t in a very loose way. In particular, to rule out polynomial size kernels, I want this parameter to be at most t to the little o of 1, meaning t by log t, polylog t, that kind of thing, but certainly not order t or more. Okay. So that's what we are supposed to do to rule out polynomial size kernels which are polynomial in the parameter size for this problem. Okay. Now tomorrow we will look at reductions of this type, where polynomial kernels may be there, but k square or k cubed, a k square kernel may not be possible, or linear kernel may not be possible. And so at that there, the leeway in this composition is that you allow it to depend on, if you make it depend on t to the 1 over d, then you say that k power d minus epsilon implies, so this implies no poly kernel, and this means no k power d minus epsilon. Okay, so today we are going to just look at a few examples. So let me start with this problem, where you are given a CNF formula, and I want to know whether there is a satisfying assignment of weight at most k. Okay, and weight is the number of ones in the assignment. And this is actually even W hard if you don't make any assumption on the lengths of these clauses in the formula. So we will assume that the length of the longest clause is bounded by some constant b. Then there is an easy algorithm, branching algorithm we saw in the first lecture, with runtime b to the k times polynomial in n. Anybody remembers what the algorithm is? So, what is the problem? You are given a CNF formula with each clause having at most b variables, and you want to know whether there is an assignment that satisfies all the clauses whose weight is at most k. How does such an algorithm go? Pick each of the variables one in clause, but it may have negated literals. But then if you set it to 0, k won't drop.
You can first process all clauses that have only negative literals.
Hmm?
You can process clauses which have only negative literals. So the budget won't be affected. I mean, they can be set to 0.
If you set it to 0, it might affect some other clause. You have to be careful.
We proved something like take clause which has both the possible and
No, because pick a monotone clause. Okay. Well, so what you said is sort of true, but don't pre-process it, sort of post-process it. Okay. So you pick a monotone clause and branch, where every clause is positive. So do a branching and saying one of this has to be true, because that's the only way you can satisfy this clause. That gives you a b-way branching, and at every branch your k drops by 1 because you have set one variable to 1, and your budget is the number of variables which you are going to set to 1. Okay. So keep doing this until you reach a stage where every clause has a negated literal. In that case, you can safely set them all to 0 because it does not affect any other clause. Okay, so that gives you a simple b to the k algorithm, and so that immediately gives you a kernel of size b to the k, right. So a b to the k algorithm is something we saw in the first lecture, and so that implies the kernel of size b to the k was in the second lecture, okay, long ago. Now, so what I am going to rule out today is that if I set my parameter to be b plus k, then I am going to say no polynomial size kernel is possible. Okay. So, we are going to design a composition like this, and so I mean this will actually really illustrate how we are going to do it, and so that is why I wanted to pick up this example. So, what is it? We are given this t instances, and the parameter is b plus k. Let n be the number of variables in each of these formula. So, each is a CNF formula, and so let us even make that all of them have our formulas on n variables. Now, this is a useful thing. I mean, actually I do not need it for the composition, but this is something very useful to know. So, if t is really large compared to b, if its t is greater than b to the k, then what I would do is I would solve each instance. So, what is it we want to do? I am going to take, so in this reduction I am going to use the same problem. Okay. I am going to take t instances of the same problem where I want a weight k satisfying assignment on each of these clauses, each of these formulas. So, it is the same problem, and if t is greater than b power k, then I claim there is a very easy way to just reduce it to the problem I have in mind. How? I would actually solve, what is it I want to know? That I want this to be an S instance if and only if at least one of this is, right. It is an R, remember I forgot to say that actually here. So, in this thing, so that Qk is an S if and only if there exists an I such that Xi is an S, right. So, I want an R of this. So, I am going to solve, so I am allowed this much time, I am going to solve each one by the b to the k algorithm, and then figure out whether the answer is, if any one of them is yes, I will say yes, otherwise I am going to say no. Okay. So, I will come up with a trivial yes or no instance and give that as a kernel. And why is that reasonable? Why am I spending time polynomial in all that? Yes, because the total time, if I brute force solve each, is t times b to the k, but b to the k is at most t. If the number of instances is quite large, then the time you are allowed is comfortable enough that you can actually solve each instance and then give you a trivial kernel. So, total time is actually t square times some polynomial in n. So, that is no problem. Okay. This is a simple thing to observe, and it helps us to bound the number of instances, but it's it's not necessary for what I am going to do. So, let us assume that t is less than b to the k. Actually, we are going to assume t is equal to b to the k. Yeah, let us even assume that the number of instances, by adding some dummy no instances, I will make sure. Yeah. Yeah. Mm-hmm. So, I will make, let us say, this is all for some simplicity of calculations. Let us assume that you are given some t instances, t is equal to b to the k. Let us even say, let us even assume that b is a power of 2. That many instances are there, not b is a power of 2, that I have an instance, and you will see why I need this when we do the calculation. So, let us assume t is equal to some, do I care, b to the k, even d to the k, where d is a power of 2. Okay, because I am going to take log and I want to make sure I get an integer and all that. So, I have so many instances. Okay, you gave me so many instances, I am going to add some more dummy no instances, because then the answer is the same. OR of that is the same as the OR of this. Okay. Okay. So, now what is it I want? I have a bunch of sat instances with some parameters, and I want this to be an S if and only if at least one of this is an S. Okay. So, let us just start with simple conjunction of these clauses and see what sort of things might go wrong, right. So, I have, think of this as a f1, f2, or I have been calling it alpha 1, but let us say f1, f2, f t, t is some power of k. These, what is it? Each one is a CNF formula. Okay. I mean, I wanted to choose this example with sort of a non-graph problem as well. So, suppose I just do a simple conjunction of all these. Let us assume that all these clauses have the same variables. Okay, just rename the variables so that they are all actually the same. They are all on the same n variables, and I just do a conjunction of this. Okay, seems like a simple thing to do, similar to the disjoint composition. What is it I want? I want, let us call this f prime. F prime has a weight something, maybe k, satisfying assignment, if and only if there exists an I such that f I has a weight at most k satisfying assignment. This is the kind of thing I want. Okay. Now, this is not really easy in either direction. Okay. If you have some fi which has a weight k satisfying assignment, if I use the same assignment, there is no reason it will satisfy any of the other clauses as well. Okay. Similarly, if I have a weight, does it work on the opposite direction? It works very strongly actually, right?
How can you just rename the variables like that? Because if there was f1, x1 in some f1 and x7 in some other guy, so if I rename x7 to be x1, then I'm
not going to rename x7 as x1. I am just saying these formulas are on the same n variables. Okay, these variables are just dummies, right? They are all on the same n variables. Hmm?
So, forcing a valuation of a variable in one instance will force that valuation.
Yeah.
But that's what we have all.
Right. Exactly. Yeah. So that. Yeah. Okay. So what were you saying about very strongly, right? So if you have a satisfying assignment for this whole thing with weight at most k, I really want one of them to have, but it's in this case it's all of them are going to have. Okay. Whereas in this forward direction, I have no hope of doing anything about it. Okay, so the and was a starting point. What do you want to do? R? Okay, let's do an R. Finally, you have to make everything C and F and so on, but let's even not worry about it. Okay, now let's see whether this works, right? So which direction works here? If I have a weight at most k satisfying assignment in one of this, then if I use the same assignment, that will satisfy this entire thing, surely. But conversely, if I have a weight at most k satisfying assignment here,
Somebody is getting satisfied.
okay, so that works, is it? So maybe the problem is that I have to make it into a CNF without blowing up my parameters. Okay, yeah. Because it's important. What is it I want? The goal I want is that my parameter k is a polynomial in my input, which is at most n. Yeah. So my parameter is b plus k, right? The size of maximum size of each clause and k. So I want to make sure that that remains controlled. Okay.
Also to convert it to CLF, size may blow up, right?
Yeah, that's exactly what you are discussing. Yeah, all kinds of things will happen. Yeah.
Size is not really a problem unless you are using polynomial type. Size you can go as much as possible.
No, okay. You also have to make sure you are spending this much time in the conversion. Yeah. So here, so what we are actually going to do so here is an interesting idea which works for many of these compositions, which is that so we will actually do a conjunction, okay, an AND of all these clauses, and ensure that if okay, so this is the kind of thing we want. So I will take F1 and F2 and Ft, but not just F1, I am going to add some more clauses. I am going to add some new variables. Okay, these new variables are going to help satisfy most of these clauses, but I also want to ensure that the new variables just don't satisfy everybody. That somehow you have the original variables. So you have on variables, let's say x1, x2, xn. I want to make sure that original variables have weight at most k. So for example, if I just add so I do an AND, that makes life easier in terms of conversions and all that. Suppose I add and b1 bar, let's call this y1 bar or y2 bar or y3 bar. For some reason, I chose some 3 variables and I add this. Okay. So then for one direction, if okay, I'm trying to sort of build intuition, I don't know how much I'll succeed. So if I for one direction, sorry,
What is it that you added?
some 3 new variables, all negated in every clause, okay, because they are sort of free, I can set them to satisfy all these clauses.
Same thing in every.
Yeah. Okay. Now that's certainly a bad idea because this is always satisfiable. Okay, with weight 0. In fact, everything can be weight 0. So now I'm going to do what is called an ID. So what I will do is that's not what I'm going to do. So there are t instances. So I'm going to introduce b1, y1, y2, y log t is sort of a binary encoding of these instances. Okay. So ultimately, in the reverse direction, if I have a weight at most k satisfying an assignment in this big thing, I want to be able to pull out, so this is the guy where it's a R, right. So, if this happens, that means R of this happens, and here is a clause which is giving me weight at most k. Okay. So, to identify which one, I am going to have an ID for each of these instances, and that is denoted by some log t variables. Okay. Now, that is where I assume t to be a nice function, so that log t is an integer and so on. So, now I am assigning log t variables. Okay. Now, for each clause in this formula in F1, in each clause. Okay. So, not just so F1 is something and something and something, right. So, let us look at F1. Okay. F1 is a CNF formula which looks like this. Now, along with all the original variables, now I am going to add its ID based on y1. So, it is basically I am going to say R y1 bar or y2 bar, because this is okay. Why don't I call this F0, F1, Ft minus 1, since it is F0, its ID is 0 0 0 0 0 0. So, all the yi's are going to appear as bar here. Okay. So, in F5, which is 5 is 0 0 0 0 0 0 1 0 1. So, all clauses here have the original things plus the y variables, that something here and the last, this guy and this guy will be positive because this is 1 and this is 1, everything else will be 0. Sorry?
Is that a single clause?
In each clause of Fi, I am going to attach this set of variables in every clause, of Fi. Okay. So, Fi every clause of Fi is going to have this set of extra variables which tells you my ID encoded with these yi variables. Yeah. Sorry? Yeah, it's exactly for the R property. Yeah, I am just building this instance. So, starting with T instances, which are F T formulas, T CNF formulas with these parameters, I am building a new formula here, and I'm doing it in an iterative step. So, what I am saying is, finally, my entire composed formula is an AND of all this. Okay. An AND of all this. So, each Fi, in every clause of Fi, I am adding its ID with this new extra variables. Okay. That is my composed formula. Let us make sure what happens to the parameters in this. So, I am done. Now, I have to prove this if and only if that, but let us see what happens to how many variables have I introduced. Log T many variables. Okay. Log T many extra variables. So, what happens to B plus K? B plus K was the parameter we started off with. This is the parameter and becomes what? B plus log T. Now, I haven't told you what is it I am looking for, right? Weight at most what? The weight I am at most is what I am looking for is K plus log T. Okay. These new variables also I am going to say weight at most log T. Actually, I am not completely done. There is one more thing I need to take care, but we will figure that out in the proof, okay, when we do the proof. So, is the construction clear? The composition is take T instances, and for each instance is a formula. It is a CNF formula with B, clause length B, whatever, and now I am attaching an ID for each clause. So, clause, it is the same set of log T variables, they are appearing in multiple different forms because of the ID, okay, the same set of variables. Okay. So, now this parameter is polynomial in the max instance size. So, that is not a problem. So, what is it now I want to show? I want to argue that f has, or yeah, finally the composed instance f has a weight at most k plus log t if and only if there exists an I such that fi has weight at most k. So, this is what I want to show. Okay. If I show this, I am done, okay, because I have spent time polynomial in the sum of the instances, my parameters are under control, it is polynomial in the max of the instance size, and I want to argue this. Okay. Now, let us see why this is true. Okay. So, what is it I am doing? I am adding this. So, if so, these extra variables may help satisfy some clauses, okay, and I want to carefully control this, how they are going to help. Okay. So, if some clause fi has a weight at most k satisfying assignment, then I am going to say, okay, use that satisfying assignment, let us see what it does. Now, I have the yi variables I want to control. Okay. Now, that satisfying assignment will satisfy my fi here without even the help of the yi variables, right. So, now I am going to set my yi variables in a way that they are completely useless for this clause, because this clause is satisfied by its local variables anyway. So, how do I set? So, if suppose it was f0, suppose f0 is a clause that has a satisfying assignment with weight at most k. So, I make all the yi's 1. So, these yi's are completely useless in terms of satisfying f0, and that is fine because f0 is satisfied with all these guys anyway. Now, by setting yi is 1, what do I achieve? I am satisfying every other class, done. What is the weight of the total assignment so far? The original k plus this log t. Okay. Forward direction is clear. That if there is a weight at most k satisfying assignment in some fi, then sorry, not forward direction, I have written in this direction. Yeah. Then my f has a satisfying assignment weight at most k plus this. Okay. The converse, I need a little bit more work. People.
For each, the ith thing, you need to have I dummy. I mean, so basically, if
So,
if the ith clause is satisfied in y's, I mean, then there will be exactly one of these clauses which is satisfied. I mean, everything will be satisfied with y.
so you are talking about the converse?
Yeah, the converse.
Okay. Okay.
So there will be exactly one clause which is not satisfied with y's.
Okay.
But that suppose that the y's, the binary there are binary ones in the binary expansion. There are say b ones. I might have I could have those b ones log
Okay,
t
so-
minus t used here. So I need to have log t minus t dummy zeros to be added in that clause. So probably some model.
Oh, you are going to change the construction a little bit. Is that what you are saying? Okay.
So I
Okay.
think in this construction it won't go through.
Okay.
So
There is a little bit more work. Let's see why, right. So, okay, what do we want to do? Suppose f has a weight at most k plus log t satisfying assignment, then see what it does to the yi values. It has set some assignment to the yi values, this satisfying assignment. Go to that particular class, these yi values give me an id, go to that clause. In that formula, yi's are useless, right, because yi's are. So, that means the original variables should satisfy them all, and what is their weight? What is the weight of the original variables? Okay. So, for the converse, if I have a weight at most k plus log t satisfy.
If suppose if the yi's have a value together, say they give a value 5, I look at f5.
So,
The one particular clause could have, so these clauses could have been satisfied because of yi's.
no, I am saying you look at a satisfying assignment which satisfies my capital F, this big composed thing, right. In that, look at the setting of yi's. Suppose it happens to be 0, 0, 0, 0, 0. Suppose, okay, I mean just pick any number you want. Then if it's all 0, 0, 0, 0, 0, 0, go to ft minus 1. That formula has all the yi variables appearing as 1, 1, 1, 1, 1, 1, 1. So, because you have set them all 0, 0, 0, 0, these guys are gone. There is one instance, exactly one instance for sure, where these yi variables are useless. How does that instance get satisfied? By the original variables. What is the weight of the original variables in that assignment? It's at most k plus log t minus whatever you have set, the yi's have set. Okay? And ideally, I want this to be k, then I am done. Right? If it's at most k, then I am done. I've got pulled my FIIs. But these log t variables, not all of them are 1. So, some of them are 0. So, I have a little more buffer. Okay. So, what I will do, so Arjun was saying some trick. So, any other simple trick to make sure, that's a problem I am saying. I do not want that. I want, because if the yi variables weights are less than log t, then I have a budget of k. So, I can't argue that there is a 1 of weight at most k. So, what I will do is the following, we will create another set of variables z1 to z log t with, and write down clauses to make sure that one of this is 1, right. So, I am going to write down I will write down the following clauses, that y1 or z1 must be true and y1 or z1 must be false, and I do this for every yi. Okay. So, essentially the zi's are the complements of yi. Okay. So, between yi's and zi's I have to spend a weight of log t. So, now I have to go, now the whole argument goes through. Okay. But the key thing about this whole composition is this idea of the ID. Okay. I have, for every instance I have an ID which I can use to pull out for the backward direction. If this entire thing is satisfied, then I look at these yi's, that gives me an ID. That gives me an ID to say, hey, that is an instance where in the original formula there is a weight at most k satisfying sign. Okay. This one? Okay. Did you understand the problem that the converse had a problem?
Yeah, there was some problem, but
What is the problem? Okay. So, let me actually go through and write. So, what is it I wanted? I want to say so if f has a satisfying assignment with weight at most k plus log t, then there exists an I such that fi has weight at most k satisfying assignment. This is what I want to show, right. So, I say okay, take this entire conjunction of f with all these extra ID variables added, and suppose it has an assignment with weight at most k plus log t. Look at its assignment on the yi variables. Okay. Based on that, I zoom in on one of the FIs and say, hey, this is a possibility that the original variables are satisfying this clause with weight at most k. That is what I want to argue. Okay. So, this has, each clause has some yi variables here, the same yi variables in that form, and I chose this fi because these yi variables are all set in a way that this clause does not help. Okay. So, my original formula is satisfied with whatever remaining weight. Okay. But what is the remaining weight? The total weight was k plus log t, k plus something. because out of this log t, if everybody was 1, I am happy. Then I am saying weight at most k and I will be done with it. But it's possible that maybe all of them were 0. So, you had a budget of k plus log t still left, then I cannot conclude this. So, what I do is create another set of variables zi's and ensure that write down these clauses as well in my composed f. What these tell you is that if y1 is 0, then z1 better be 1, or if y1 is 1, then z1 better be 0. So, yi and zi's are complements of each other. Okay. So, that tells you that okay, you did not spend all your weight on the yi's, but then you have to spend it on the zi's. So, between yi and zi, the total weight has to be log t. Then you are left with a budget of k and this. Okay, good. Now, okay, doesn't help. I don't know what. Yes, what I described, but in a slightly different form. So, I am going to move on to here. Okay. So, let us move on to a different problem. So, the key thing I want take away point is this idea of ID, okay, and it manifests in multiple different forms. So, the next problem I want to talk about is a nice graph problem, which is given a graph, are there k disjoint cycles? Undirected graph, k vertex disjoint cycles. Okay. Now, this is the FPT due to some is that the only algorithm or any other? I don't know. Okay. Okay. So, it is very close to feedback vertex set, right. So, if suppose I run my FVS algorithm and no, yeah, if it comes back saying yes, there is a feedback vertex set of size at most k, then what can you say here? What is the answer to this question? Okay, let us ask this. Okay. If FES size is at most k, then it is a no instance, because if you have k vertex disjoint cycles, you need one to kill one vertex from each of this. So, feedback vertex set size is more, then it is no, else you need some more work. Okay. There are some famous combinatorial theorem which talks about some sort of a min max between if the feedback vertex set size is if you have more less than or equal to k cycles, then the feedback vertex set size is not much more than k. And so, I am not going to prove you except to say that this is FPT and by k power k 2 to the k, I do not know. So, I think there is a 2 to the k algorithm, and we want to rule out polynomial size kernels for this problem. And but instead of directly trying to develop composition for this problem, we are going to start with an intermediate problem, develop composition for that problem, and then do a reduction, a parameterized reduction from that problem to this problem. Okay. So, this is an example where we will have a non-graph problem, we will talk about reductions, parameterized reductions and so on. Okay. So, the intermediate problem is the following. Oh, clearly you will recognize the handwriting of the slides. Let Lk be an alphabet consisting of letters 1 to k. So, the problem is disjoint factors, and what is the problem? You are given a string like this on this characters 1 to k, and what is a factor? A factor is a substring which starts and ends at the same character. Okay. So, that for example, is a 1 factor. It starts at 1 and ends at 1. So, that is a 5 factor, and what we are interested in is finding disjoint factors, and disjoint factors are factors that do not overlap, and this is the problem. Given a string on this k letter alphabet, question is, does this word have all the k factors mutually disjoint, and the parameter is k. Okay. Can we think of a simple FPT algorithm for this first? So, we are interested in finding factors starting and ending at every character, each of the k characters, and is there, and they all have to be disjoint. So, suppose I tell you the order in which these factors, suppose it is an S instance and I tell you, oh, factor 3 comes first and then factor 7 and then 4 and then 5. Suppose I tell you that permutation, then can you come up, can you find that? Just once can, because the first 3 you will take it, and first time it ends, there may be actually another factor, but you are better off taking the first 3. Throw that out and then go and find the next factor and so on, linear time. So, does that give you an FPT algorithm? K factorial, right? Run through all permutations and see whether there is one. Okay. Now, it turns out there is also a simple dynamic programming algorithm, which gives you an algorithm of this type 2 to the k p n. So, now we are going to design a composition. We are going to say that this problem does not have a polynomial size kernel, k is the parameter, and here again, since we have a 2 to the k polynomial time algorithm, it immediately bounds the number of instances for the composition algorithm, because if t is large, same idea, you have enough time to try and solve each one of them and give a trivial kernel, whether it is S or no. So, let us assume t is at most 2. I mean, again, this is not really necessary for the composition we are going to do, but again, the composition we are going to do is very similar, some sort of an ID attachment to each of these instances to pull out where these k factors are coming from. Okay. So, let us start with t instances, each is a word over this k letter alphabet. We are going to think of these instances as leaves of a binary tree, a complete binary tree. Okay. Okay. So, even in the earlier instances, the formula problem, you think of it as I am attaching one variable at a time. Okay. This has a similar kind of a flavor. So, there are t instances, let us assume t is a power of 2 by the same kind of an argument by adding some dummy no instances to make it equal to 2 power k. So, what we are going to do, the goal is to come up with a huge string, right? Each one is a string. The goal is to come up with a big string such that that big string has disjoint some f of k factors, if and only if one of these strings has a k factor, disjoint k factor. Okay. So, what we are going to attach some dummy variables. So, everybody in this level. So, eventually we are going to add t, which is 2 power k. So, log t, k extra characters to our alphabet. So, everybody at this level gets a character b0. Okay. So, I am concatenating. So, what is the idea? We want to make sure that 2 strings together combine and get a factor, right. I want to make sure that if k factors exist, then they are all, at least for the original ones, they are all coming from one string. Okay. Sorry. So, we are going to add some extra characters, so that if you just trip over and combine things, then you are going to have a problem of overlapping things. Question? Okay. So, we are going to, this composed string will show up at the root of this tree finally. So, we are going to add this character B0 at every node, every instance in the leaf, B0 before and after. In general, at the inductive level, if I have this string here and this string here at the parent, I attach a new character Bj for that level j, and then concatenate this and attach a Bj before and after. Okay, is it clear? Okay, so how many? So I have added k extra characters, right? K was my alphabet size. Now it has become 2k. The original k plus this B0, B1, B2, Bk minus 1, because the number of instances was 2 power k. So here is a claim: the composed word has all the 2k disjoint factors if and only if at least one of the inputs instances is all the k disjoint factors. Okay, especially for this direction, if you have 2k disjoint factors, then you can just take a look at and see how they are all forming, and it's going to just give you an ID to one such instance and say, hey, that's where you have to get your original k disjoint factors. Okay, we'll see that. It's a very simple proof. So here is an example with 8 instances. So if P, Q, R, S, W, X, Y, Z are the leaves of this tree, B naught is a character attached to each of those at this level, and then we attach B1, then attach B2, and we probably do not need to attach a B3 here at this root. So this is the root and this is the composed string. The claim is that this string has all disjoint factors if and only if one of those strings has k disjoint factors. Okay. So if you carefully look at this composed string, how do I get a factor of B2? Well, here is a factor of B2, or there is a factor of B2, right. There are only 2 factors of B2 possible here. Okay. So, suppose, okay, let us see, suppose I say, okay, this is the B2 factor I am going to pick up for my solution, because I need a factor for every character in my new alphabet. So, if I manage to pick up this B2 character, B2 factor, then since the factors have to be disjoint, all other factors should come from the other side. Okay. Now, let us see, where do I get B1 factor? I can't get it here because I already used it for the B2 factor. So, B1 has to come from this portion of it. Okay. Here again there are 2 B1 factors, there is one which is this or this B1 factor. So, suppose I decide to choose this for my B1 factor, then where is the B0 factor going to come from? Well, it has to come from, there are 2 choices, and I have one of those to pick my B0, and if I manage to pick this B0 factor, then all my factors on the original alphabets all should come from here. Okay. So, essentially in the case of the formula, the settings for the yi's told you which fi you should zoom in and find your original min wide satisfying assignment. Here the setting, the factors for B naught tells you where you can get. So, this whole thing is proof is reversible, it is an if and only if, and the parameter now has changed from k to 2k, because the log of t, number of instances is what I have used, k to 2k or k plus log t, and so that is it.
Here the assumption at the beginning was you can assume the number of words is 2 power k.
You do not even need that assumption, do not worry about it. So, I am just saying the parameter has gone from k to k plus log t. Put these 2 t instances of the leaves, draw this complete binary tree, that height is log t, and I have introduced one character for each level. Okay. So, this is what we have shown. The composed word has all the 2k disjoint factors. So, it is again the same idea of this ID distributed in this fashion. Questions? Okay. Now, let us just go back to vertex disjoint cycles. This was the original problem I was interested in. So, I do not know of any composition for this problem to rule out polynomial size kernel, but it turns out we could choose an intermediate problem, run composition, rule that out and give a reduction to this. It is a very simple reduction. Okay, before that something about this problem related to FES. Instead of vertex disjoint, if you ask edge disjoint cycles, surprisingly that has a polynomial size kernel. Okay, again simple exercise. So, here is a reduction from disjoint factors, very completely trivial reduction from disjoint factors to disjoint cycles, right. You are given a string and you want to know whether there are k disjoint factors here. I am going to draw this graph, lay the entire string in a path, then add an extra vertex for one for each character, and we will draw an edge I to all the vertices that are I here. Okay, so, in this string. So, 1, 1, 2, 3, 3. So, 2 is adjacent to a 2 here, this 2 here and this 2 here. So, if you have k disjoint factors, if and only if there are k vertex disjoint cycles, right. One direction is easy. If you have k vertex disjoint cycles, since this is a path, pick any cycle, it should contain exactly one vertex from here. So, pick that, let us say it was I, then I was adjacent to only I. So, the other two endpoints, that should give you a factor. Okay. So, here is an example of where you can use, if not composition, but parameterized reductions to rule out polynomial size kernels. Okay. So, now I am going to move on to my last example, which I will do on the board. Oh, I may actually need. Okay. So, the problem I want to look at is the clique problem. So, clique is a hard problem anyway, W1 hard problem. So, but just like we were having fun giving composition for independent set, you can actually give composition for clique as well, right. In fact, disjoint union works perfectly well. You have take t instances where you want to find whether there is a clique of size k, put them all together and you know that this whole disjoint union has a clique of size k if and only if one of the instances has a clique of size k, right. So, a trivial polynomial kernel, ruling out polynomial kernel, but we knew that anyway because of W1 hardness result. And just like how did we make use of this independent set? Okay, we said we will parameterize by tree width, and disjoint union maintains tree width. So, that immediately tells you that clique parameterized by tree width has no poly kernel. Disjoint union, right, take your graphs, tree width. So, what I am going to do is slightly a stronger result of this, and that is not tree width, but vertex cover. Okay. So, what is the problem? You are given a graph, and the vertex cover S, and the question is, does G have a clique of size at least k? The parameter is not the clique size, but the parameter is size of S. Okay. Now, this is I mean, we've seen a lot of examples. I mean, initially we started out with solution size as a parameter, right? Vertex cover of size k, feedback vertex set, directed feedback vertex set, and quickly we moved to various other parameterizations. Tree width was one which was looked at. Now here we are looking at vertex cover size as the parameter. Okay. Now we know that vertex cover number of a graph is at most, so no, tree width is at most the vertex cover, right? So in the FPT algorithm, now I am giving you right. Yeah, so this is a negative result. So now I am saying I am giving you this much as a parameter, and we are saying that even with that larger parameter, you can't get a polynomial size kernel. Okay. So for positive questions, smaller and smaller parameters are useful, because then you want to say, you get tighter results. For a negative question, we are saying even with larger parameter like this, there is no chance of a polynomial size kernel. Okay. But this is very mysterious, because let us say, suppose how does a graph look like? If you have a vertex cover of size k, we know that, what do we know about independent set, right? This is independent set. So what can be the size of the maximum clique? Maximum k plus 1, right? So immediately it gives you an FPT algorithm. What is the FPT algorithm? Try all subsets of this this vertex cover, and you can at most add 1 to see whether there is a clique of size whatever. Maximum, that's all is possible. So k plus 1. So FPT algorithm is very trivial. The graph is very well structured, and so you can also talk about, okay, you're going to rule out one kernel. Can I have multiple kernels? Okay, that's another direction of work in this context of kernelization, where I want to look at what is called Turing kernel. So here, for example, I could say, here is a kernel. Your clique could be sitting here. The maximum clique. So I can reduce the problem and say the maximum clique could be sitting here, or here, or here. So I am giving you a k plus 1 sized kernel, but not one kernel, but n kernels. Okay. So this is another direction of work where you say, okay, wherever I have ruled out polynomial kernels, can I get multiple kernels? Okay, Turing kernels and so on. So in this case, there are lots of kernels. FPT algorithm is simple, but we are going to say no single polynomial size kernel is possible by giving us a reduction or a composition, and the reduction is going to go from the following. We are going to reduce from the standard clique problem to this problem.
So how we combine the solution to the multiple kernels?
Oh, the multiple kernel? All we are saying is, if you are looking for a max clique, right, in this problem, it's going to be sitting in this set, right? I've compressed the problem and saying k plus 1 sized. This is k plus 1 sized, or sitting here, or sitting here. So I'm giving you multiple kernels of size k plus 1, or yeah. Okay, so here is our goal now. Hopefully, in another 10 minutes it should be done. So what are we going to do? We have t instances, G1 and L. Let's say I'm interested in L clique.
That's not what you normally call as multiple kernels, right? A kernel is something which guarantees that solution is sitting within D. Now, the solution is going to reside within one of these, right? So this is not multiple kernels.
I'm just going to call it. What's your problem? It's a definition. I'm new notion, right? It's a new notion. It's a new notion. So I have t instances, and I want to reduce to a g prime. What do I'm allowed polynomial in the size of these instances, and I want to have a parameter which let's call this to be the parameter, and this is, remember that this parameter is size of the vertex cover of G prime. And then I am going to have the property, the equivalent instance I want, which is that G prime has a clique of size something, which is again polynomial in max of the input. No, sorry, this need not be polynomial in max, only this is the parameter. So, this has to be polynomial in n. So, if each one has n vertices, let us say it is going to be about polynomial in n. This I am going to have G prime as a clique of size this, if and only if G has a clique of size L. Sorry, yeah. Thank you. Yeah, if and only if there exists I such that Gi has a clique of size L. Yeah. Okay, so let me just, you have probably seen enough W1 hardness results that you will come up with one yourself, but so I am just going to just give the reduction without talking too much about the intuition. So, this has an L by N matrix. So, okay, then let me write this number. So, each Gi has n vertices. What is it I want to write here? It's going to be L plus n choose 2 plus 1. Okay. And this is going to be L plus n choose 2. So, it is polynomial in the max input size. Okay. So, the goal is to find a clique of this size. Okay. So, that is what we are going to do. So, I have my graph T Gi is given there. So, all on the same vertex set. So, let us think of this. I have some NL vertices here. And the adjacency is going to be all edges except those within a row or a column. Okay. So, there are NL vertices here, and if you have two vertices in the same column, I am not going to add an edge. Similarly, if there are two vertices in the same row, I am not going to add an edge, every other edge is there. What is the max clique size possible here? So, L is much less than N. Okay. So, what is the so L is much less than N, L is this L. Okay. So, I can only have a clique of size L from here. Okay. Now, that is going to contribute to this L. Okay. In fact, these L vertices which I am going to L rows which I am going to pick, whatever columns, they will determine what is that clique in that Gi which I am looking for. Okay. So, this is, you can think of it as a clique selector. And then I have a vertex for each instance, and that is all of them are going to be adjacent to these guys. And then I have some three
U1 is connected to what? All the
every UI is connected to all these NL vertices. Yep. Okay. And so, and I have some Wij bar, let us call this These are the edge selectors W, I bar, J. Okay. So, these 3 vertices for all pairs I j. Yeah. So, that is it about the vertex set. Okay. So, just to reassure you that I am done at least with the vertex set. So, it is NL vertices here, and I have how many vertex set here? 3 into n choose 2 vertices here, and there are t vertices here. That is all the vertex set is. Now, I have to define adjacencies between ui's and wij's. These wij's are adjacent to all of these guys. wij bar is adjacent to all of this except j bar. So, except jth column. Okay. So, this is all except jth column, and this is adjacent to all except ith row. Okay. Ith row. Ith row.
But there are only L rows. I don't know.
There are only, I see. You think it's column? Huh. Yeah, okay. I think it's column. Yeah, you may be right. I'll just check. Yeah. And then we're going to add all of these form a clique. In fact, there are edges between all of this, except for each row, there are edges across. They are all edges, yeah, except for these rows. Right, except for each row, there are edges across. So, what is the max clique size possible here? N choose 2, because you can't pick 2 from a row, because there are no edges. Okay. So, the max clique possible is n choose 2 here, L here. So, that is even without looking at the graph, you are guaranteed about this much clique size. So, it is the extra 1 which is going to determine your, the rest of the whole thing. Okay. Okay. Now, the last bit I have to tell you is this construction, that ui is adjacent to which of these vertices. Okay. Each ui is representing a graph, the original graph, right, an instance of the graph. So, I am going to say a ui is adjacent to wij if ij is an edge in this graph, and otherwise to these 2 vertices. Yeah. So, this is the one which is actually saying which edges are present in each instance. So, ui is adjacent to wij if ij is an edge, and otherwise to these 2 vertices. Okay. So, that is the end of the graph. Okay. So, what is the size of the vertex cover here? The top part is independent. So, everything else form a vertex cover which is of size L plus 3 n choose 2. So, it is not n choose 2, but L plus, but still polynomial in n. So, it is oh, you are right, yeah, yep. So, it is about n square. So, it is all fine. Okay. So, our goal was to make sure that the vertex cover, okay, just to step back, we said disjoint union works for clique and all that, fine, and it helps to maintain the tree width, but it does not maintain the vertex cover size. That was a problem. Vertex cover size will blow up by t times and so on. So, all this heavy machinery is doing is to make sure the vertex cover size remains independent of t, only a function of the input size. Okay, so now I think the rest of the proof you all figured out, hopefully. So now I want to say that some GI has a clique of size L if and only if this whole graph has a clique of size L plus n choose 2 plus 1. Okay. And we already observed that L plus n choose 2 is all you can get from here. It is that pulling that extra 1. Okay. So, if some GI has a clique of size L, what I will do, I will take that UI and pick the clique, the L vertices, they will determine which column I pick. Okay. The first vertex will be vertex number 3, second vertex may be vertex number 2, third vertex may be 79 or whatever. That L clique forms these vertices here. The L clique in that graph form this. Okay. So, I will get a clique of size L here plus 1 from there. Now, where do I get a clique of size n choose 2 here? What do I pick? Because I have to make sure that clearly there is a clique of size n by 2 here, but they have to be adjacent to these guys. That is my worry, right. So, for all edges in that clique, I will pick the Wij's. Happily, they are all adjacent to these guys as well as to UI. For non edges, UI is adjacent to them anyways. I am going to pick one of this, and I claim that one of this will be adjacent to all these guys. Okay. And that is because if I pick an ij bar, it is going to be non adjacent to jth row or jth column, and this is non adjacent to ith column. And I know that I or j is certainly not in here, because ij was an edge. No, sorry, ij was a non edge. When ij is a non edge, in this clique I or j is not there. So, I have no problem picking an appropriate Wij's, which will be adjacent to all these guys. Okay. And the converse is very similar. We just say that if you have a clique of size L plus 1 plus n choose 2, the clique has to exactly look like L from here, n choose 2 from here, and 1 from there. And we will say that that guy will be what you pick here will be a clique, and that is the clique in UI is what you have to. We will just sort of reverse this proof. Okay. I don't want to bore those who are not following this. I will stop here, and if anybody is interested, we can discuss the reverse direction 5 more minutes afterwards. Lunch break.